Okay. Uh, so this is thermodynamics. Let's go. Question number one. A sample containing 2 mole of helium gas originally at some temperature at some pressure is cooled to its normal boiling point at 4 Kelvin. Okay, condensed to a liquid and then cooled further to 2 Kelvin. So just have this container with 2 mole helium gas. Helium is basically like an ideal gas. Um, right? No interactive forces in between these. It's small, right? It's a small molecule. Originally at, I mean, yeah, like it is, okay, whatever. Just move on. Originally at 298.15 Kelvin, which is approximately 300 Kelvin. 300 Kelvin, and then you change this to, and it's 1 bar. Um, so a bar is like 1 atmosphere, right? So it's just 1 atmosphere. And it is cooled to its normal boiling point at, yeah, I think 1 bar is 1 atmosphere. Okay, and it's cooled to its normal boiling temperature of 4 Kelvin. So now it's at 4 Kelvin. It's still 2 moles condensed to a liquid and then cooled further to 2 Kelvin. Oh, so it's converted to a liquid, huh? Okay, so it's now a liquid. It's still 2 moles, but now it's a liquid. Okay, so there it undergoes another phase transition to second liquid form called helium-2, whatever that means. A beam of laser light suddenly vaporizes this liquid phase and the helium is brought to a temperature of 298.15 Kelvin. Oh, uh, so it's just cool. Is its pressure changed? No, it's not. So its pressure is still the same, huh? Right, then it's condensed to a liquid at 4 Kelvin. So you can say like this complete thing, if this was like a piston, then this thing is still 1 atmosphere. Its pressure didn't change, it's 4 Kelvin, it's still 2 moles. Right. Cooled further to 2 kelvins. Right, so you will need the work first of all, like done on this. And for that, you need to apply the ideal gas. So till 4 Kelvin, it's just an ideal gas. So yeah, you can figure out what that volume changes, and then do 1 atmosphere times that, and that will be your work. First phase transition, the second. Right, a beam of laser light suddenly vaporizes the liquid phase, and the helium is brought to a temperature of something. Wait, what? We just want the entropy change. Like, why did you go through this whole process when at the end you just want to convert this back to 298.15 and pressure of 0.5 bar, so it's half of what it should be initially, right? Yeah, so it's just that the pressure changed, temperature is still the same, so whatever volume it initially had, it just became 2 times of that. So your entropy became like, what is your entropy? Your entropy is like, for an ideal gas, we define it like this. NR, so this is proportional to N R natural log of Vt power F upon 2 upon V naught T naught power F upon 2, where V naught T naught is a state such that S is 1. Sorry, such that S is 0. So I don't know what that is. But yeah, this is how the entropy changes, right? So you are basically like, remove all this process in the middle. It's just you have this 2 mole thing, and now it's going to, right? So some volume, say V naught, then this is going to V naught upon, sorry, V naught times 2. So 2 V naught, and now it's like this. Or I should say this is delta S, whatever, who cares? It's still at 300 Kelvin, same temperature. Now it's at 0.5 atmosphere, right? So yeah, it's just going to be nr natural log of 2, because v upon v naught is 2 and t is still the same. So that's it. That's our entropy change, of course. So it's going to be 2 moles into r. R is, so you want in joule per Kelvin, right? So you want to put in SI. It's like 8.3. Into natural log 2. Natural log 2 is like 0.69 something, which I'm going to say is 0.7 approximately. So this is what? 16.6, which is point so 00, and 2 4 get it on, it should be 41 seconds to 6, and then 4 get it on, and then it's 11. So 11.62, that is the thing, which is, yes, it's close to 11.5. And yeah, the entropy increases, so the total change is positive. So first A. Right, next question. Seriously thought this would be very hard, but no, it's just this, all of that's just a distraction. The area under the plot of Cp versus T curve, okay, versus the absolute temperature T is directly proportional to what? Under a plot of Cp upon T curve, okay, versus the absolute temperature T. I mean, why would you want to find that? Does this even make sense? It's directly related to delta S maybe. I mean, you have this 1 upon T over here versus the absolute temperature, so you're multiplying by dt, and like what, you know that ncp delta T, that is your delta H, so you can write this like dt equal to dH and stuff, and then this thing upon T, that's just dH upon T. So at constant pressures, dH upon T is your entropy change. But yeah, like if it's not a constant pressure system, then why would you have this? Okay, this is definitely not any of this thing, you know. Is it Q? No, it's not. Is it delta H? No, like you want to find the actual like integration of that. So why would you do this? At max, it can be entropy, but that's only um, that's only at constant pressure, right? So or if like your initial and final pressures are the same, then you can say that yes, dH upon T, that just integrates to delta S. Yeah, like this makes no sense, but we have to go for it. You know, it's J. They don't ask such that it would make sense. They ask such that it would not make sense. Question number 3. Question number 3 is we consider growing plant, what? Limiting our system to the plant itself. Okay, fine. To be an example of decreasing entropy. Small molecules like what? Decreasing entropy. Huh. Carbon dioxide, waters, okay, are built into complex but orderly arrangements of the macromolecules. Which one of the following statements apply here? Second law of thermodynamics, that the entropy of the universe is increasing, is being violated? No, it's not. Right? It's not being violated because we just consider the entropy of the system. What about the surrounding? Plant growth is so complex, it is loss of seriously. Come on, no, B is just wrong because the plant itself, like if you cover this by say a container and then forget that there's a plant inside it and just say it's the system, that's the container basically, then yeah, you can apply thermodynamics over here. Why should it be? No, he is just not correct. Right. System second law of thermodynamics is not being violated because entropy of the plant surrounding is increasing. Yes, that's correct. The second law of thermodynamics is not being violated because entropy of the plant surrounding is decreasing. No. Look, the entropy of the system over here, so it's going from gaseous molecules to like liquid or solid or something like that, and that means your entropy is decreasing for the system, right? So what are we considering into the system? We are just considering the molecules that uh, that were now, like before they were not part of the plant and now they are. So that thing, like, yeah, and we are also considering the plant itself. So that is our system. So definitely the system's entropy is decreasing, and that means. But wait, you are considering only the plant with the system. No, then that's kind of. But you are saying that it is decreasing its own entropy. But how does that even make sense? Because it's like its own matter is increasing, the plant is growing. So yeah, like its entropy should in fact increase. But hey, it's J. They don't ask questions to make logic. Right. So I think C is the correct one. Question number 4. Which of the following statements is true? For every process in an isolated system, delta T equal to 0. Isolated system, there's no heat change, um, there's no matter exchange. I mean, no, this is not right. Like, what about things like, I don't know, like reactions that happen automatically? So spontaneous reactions, those increase the temperature of the system. Like, look at sun, for example. Yeah, the star, sun, its temperature is definitely um, not decrease. Okay, so not just the sun, because that would be a problematic thing, right? It is gonna radiate stuff out, so it's not isolated. So maybe like just consider the sun and another. It's like this is a very big spherical mirror where the mirror side is like inside of this surface, the inside side of the surface, right? That's the thing. And of course the sun is just radiating out stuff, so now its temperature will increase because it's, yeah. And that's like, okay, this is a very complicated example. Just consider some exothermic reactions like a burning firecracker, right? It's an adiabatic expansion, right? So like burning something in like a piston, for example. When you burn this, it happens so fast that it doesn't get the time to exchange heat with the surrounding. Neither is this exchanging any kind of matter with the surrounding. So like this happens in combustion engines. So it's approximately adiabatic. So yeah, here the temperature does increase. What's the big deal about it? Like, no, delta T is not zero all the time. Delta S is zero. No, no. Consider the universe itself. It can be considered as a very big system, and its delta S is definitely just increasing. So no, B is wrong. And of course, for any isolated system, if it's like having spontaneous reactions inside it, delta S will increase. For every process in an isolated system that has no macroscopic kinetic or potential energy, delta E is what? No energy. Process and energy. You mean energy change? Delta E is zero. Macroscopic kinetic or potential energy. What about the chemical energy? Is that not potential energy? And is that macroscopic at all? I don't think so. So C is weird. I don't know what it means. If a closed system undergoes a reversible change for which delta V equal to 0, then PV work is 0. Yes, D is very true. Right? The following statements is false. The quantities E, H, and G have the same dimension. Yeah, it's energy. This is also energy. This is also energy. So yes, this is true. So this is not false. In case of reversible chemical reaction, gives free energy reaches to its minimum value when the equilibrium is established. Yes, that is true, but for only constant pressure temperature systems do we actually take Gibbs free energy into consideration. So I don't know. Looks true at least. Gibbs free energy of 10 gram ice at something and 1 atmosphere. So basically the melting point is less than the Gibbs free energy of, no, both are equal because that is the melting point. That's when this is in equilibrium. So yeah, the Gibbs free energies are equal, right? The pressures are the same and stuff. So yes, that is the thing. The quantities STT, TDS, VDP, and this integration are all having the same dimensions. So which of them is wrong? I don't know. STT and TDS, of course, they have the same dimension. So it's just heat, right? And heat is basically work. And VDP is like the same thing as PdV, but PdV is also work. And this integration, this is also work itself. So yeah, they all have the dimensions of energy. Yes, D is correct. C is incorrect, right? So yeah, this is the incorrect one because it is equal. Question number 6. Which of the following is correctly matched? Reversible melting of benzene at something and normal melting point. This. Okay. 1 atmosphere, normal melting point. Oh, okay. So when it's reversible melting at some atmosphere, okay, and normal melting point, then that means it's just the equilibrium process, of course. So for that, Q is bigger than 0, W is bigger than 0, delta E is bigger than 0, it's actually 0. Solid benzene melting, of course, you need to provide it heat. We need to, well, is it doing work though? I would think like solid benzene to liquid benzene, is there a change in the volume? That's the only thing that can tell us about the work. If there's a change in volume, that means work is being done on the system. That, yeah, maybe because in chemistry you put the work into the system, it is out of the. So yeah, delta E is bigger than zero. I mean, yes, I think. Okay, but is it? I don't know. Delta H is bigger than zero. Yes, if Q is bigger than zero, delta H is also bigger than zero. This guy, not so sure about it, but it looks correct. Residual melting of ice at 0 degrees Celsius and 1 atmosphere. Q bigger than zero, W less than zero. So we know that ice is it has bigger molar volume than water. So when it changes, what happens is that the volume decreases for the system, and there's work done on the system, right? Over here, the work done on the system will be oh yeah, this will be negative. So maybe A is incorrect, but it could be that solid benzene has, like, it's also anomalous like water. Who knows? So B is like, no, this is kind of wrong. W less than zero, that shouldn't be happening. Okay, I think this is incorrectly matched. And in that case, maybe A is also incorrectly matched because might be it's not anomalous. Okay, delta bigger than zero, delta H bigger than zero. Okay, fine. Reversible adiabatic expansion of ideal gas. Adiabatic. Okay, Q equal to zero. Yes. W, well, it's expansion. So you like, yeah, the surrounding is doing negative work on the system. That's why W should be less than zero. So this is definitely incorrectly matched. Delta E less than zero, delta H less than zero is expansion. So Vt power F by 2 is constant. That means like F by 2 is kind of a positive constant, right? Sorry. Um, a constant bigger than 1. Yeah, that's better. And that means your temperature is somehow inversely related to your volume, right? So when your volume increases, so temperature decreases. So delta E and delta H both be negative. Yes. So this, yeah, I mean, okay, but W bigger than zero. How does it even make sense? Adiabatic expansion of perfect gas into vacuum. Into vacuum, huh? So Q equal to zero. Yes. I mean, there's nothing that can give it the heat. W equal to zero. Yes, there's nothing that's working against its expansion. Delta E equal to zero. Of course, I mean, like, where will the energy go? It can't radiate directly, right? I mean, we are not taking that into consideration. So no, delta E is zero, in fact. It's not positive or negative. Delta H is zero, of course. If delta E is zero, then gamma times that. So it's also zero. So D works. D. 7. When an open glass of water is cooled from this to this by putting 50 degrees Celsius glass of water in a bath that is at 20 degrees Celsius. So it's cooled from 50 to 20 by putting 50 degrees Celsius glass in a water of bath that is at 20 degrees Celsius. Okay. The absolute value of the entropy change in the bath is. So, okay, the bath and the glass are different, I think. Right. So then the absolute value of the entropy change in the bath. So, you didn't give us a mass or anything. Is something the absolute value of entropy change in glass of water. So, okay, absolute value, that's just a magnitude basically. So it's like you got this 50 degrees Celsius water over here, and you have this 20 degrees Celsius water over here. What do you know? You know that like heat is gonna flow from here to here. That means, let's say this thing is Q flowed into it, then minus Q flowed from it, or yeah, something. Okay, Q flowed from it into it. Then its entropy change, that's just Q upon 20 degrees Celsius into Kelvin. That's like 293 Kelvin, whatever. Yeah. And this thing is going to be negative Q upon 323 Kelvin or something like that. So the thing is, this thing is positive, right? And that's because this thing Q upon 293, that's bigger than Q upon 323. So yeah, for the bar, the absolute value is bigger than what is for the glass. So it's greater than 7th A. Alright, next. Question number 8. An ideal gas expands from volume V1 to V2. This may be achieved by any of the three processes: isobaric, isothermal, adiabatic. Let delta E be the change in internal energy of the gas, Q be the quantity of heat added to the system, W be the work done on the system. So what's it? Expands from volume V1 to V2. So different processes: isobaric, isothermal, and adiabatic. You have three different processes. Okay. Delta E be the change in internal energy of the system. Okay, let's look at the options. Delta E is the least in adiabatic expansion. Well, if it's adiabatic, there's no heat in it. It's just okay. So it's V1 to V2. Hmm. Right. Isothermal, there is no change in energy at all. And isobaric, there is change in energy. It's just like change in volume is proportional to change in temperature. Okay, we should do it now. For isobaric, you know what? Like this is so stupid because in isobaric you could change your pressure and then this would just be different. Like because temperature is also proportional to pressure. So yeah, like what? Why would you? And it's just V1 to V2, but there could be so many different states going from here to here, right? Yeah. So delta E is the same for all of them if these states are the same, but are these states the same? No, they are not. How would you tell anything if you don't know like what the initial state even is or what are the conditions for these three? I don't know. And are these like reversible or irreversible? J doesn't make sense. Keep on going. So volume, it's just V1, and now it's going to V2. Your pressure temperature, we'll just say it's V1, V2. So then in isobaric, it's just the same thing. Okay, sorry, it should be T1 earlier. Let's go for isobaric. If this is isobaric, then your temperature will just be V2 upon V1 times T1. So your delta E will basically just be V2 upon V1 minus V1 into minus 1 into T. That's our delta T, sorry, T1. That's our delta T1 thing. I mean, you should give at least one of these or like the moles or something like that. Right? But you gave nothing. So, okay, isobaric is the thing and that terms like an R. Okay, what about adiabatic? For adiabatic, just have Vt power F upon 2 equal to constant, right? So your temperature is just like, okay, T2 upon T1, that will be V1 upon V2 to the power of 2 upon F. So yeah, this will just be V1 upon V2 to the power of 2 upon F minus 1 T1 and R. Now we don't know if V2 is bigger. Okay, it's expand. So we will just say that yeah, V2 is bigger. Fine. If V2 is bigger, then this thing is positive, of course. What about this guy? So V1 upon V2. Oh no. You know that thing, right? Where adiabatic expansion like that cools the gas. You must have seen it, right? So when you have like a bicycle pump and you compress it forcefully, you're doing it adiabatically basically. Then this like heats up and your pump starts to heat up as well. And of course it escapes. So then yeah, that's not a problem. And then when you pull it up, the air is coming from here, and that's why it's not heating up. Sorry, that's why it's not cooling it, and so your pump keeps on heating. But if you're like if you close this and then you keep on and also close this both the valves and then you do this thing, you'll see there's no temperature change because it just heats up when you compress, and when you pull out it cools. So yeah, when you expand, automatically it cools. That means this is going to be negative. So of course Isobaric more than adiabatic, and isothermal is 0. So first isobaric, then isothermal, then adiabatic for delta E. So it's the greatest in isobaric, and it's the least in adiabatic. In between the values of another isobaric. Okay, so which of the following is not true for E? So delta E is the least in adiabatic. That is very correct. Delta E is the greatest in the adiabatic process. No, that's incorrect. So B is the way. Delta is the greatest in under isobaric process. That is very correct. B is also correct. Okay, ninth. Alright, ninth. Arrange the following reactions in order of decreasing delta S not standard. Okay, values. Oh yeah, this thing. So it's like 2 to 2, not much. Just not much entropy change. 3 to 2, that is an entropy change. So it's a negative entropy change. And this is 1 to 2, that is a positive entropy change. So third bigger than first, bigger than second. That's D. Okay. Question number 10. Use your understanding of thermodynamics to predict the signs of delta H and delta S of the following reactions. So 3 moles to 2 moles and in gaseous. So the cool thing about entropy is like, what was I gonna say? Yeah, it like heavily depends on the number of moles in that container. So yeah. And over here it's going from 3 to 2. That means that delta S is probably decreasing, right? There is of course that entropy of these molecules themselves, like H2 only has some degrees of freedom, O2 only has some degrees of freedom. This thing is like it can rotate in a lot of different ways and stuff, and so might be its own entropies or entropy of the molecule is like maybe more, but the moles are different, right? The moles are smaller, and that means your entropy is probably decreasing. So delta S is negative, I think. And what's your delta H for this? So it's combustion basically, and that means delta H should be negative as well, right? Yes. Yeah, so delta H negative, exothermic. Correct. A, I think. So the following statements is false regarding the reaction A reversible with B. The reaction can achieve the lowest possible free energy by going to completion. No, no, not to completion, going to equilibrium. That's when delta G is. So that's when G is the minimum. At equilibrium, delta G is 0. Yes. At equilibrium, GA equal to GP. Yes. So false regarding only X. C. And of course, like here delta G, it should probably be dG, but we say delta G because we want like per moles, or right. So this is not like this is not actual, this has no physical meaning, all right? It's just a very scaled up version of dG. Does that make sense? Consider the reaction below at 298 Kelvin. Graphite plus H2 gives CH4. Okay, so you're trading 2 moles, so like 2 gaseous moles for 1 gaseous mole. I think delta S is negative. Oh, what's this thing? Delta H formation for this reaction. Okay, delta S kilojoule per mole. Why are there 3 values for this? Misstatement about the, okay. Delta G of the reaction is this thing, and the reaction is driven by enthalpy only. Why are there 3 of these values? Oh, so this is for carbon, this is for like H2, and this is for graphite. Fine. So what's the delta S in this case? Right, this is entropy. This is not delta entropy. So 5.6 plus this guy, that's just 136.3, which is less than that, right? So your entropy increases. What? Seriously? Like this has less entropy, kilojoule per mole. Okay, so 2 of these. Okay, then it should be like 261.4 plus 5.6 minus 186.3, and this is like what? It's gonna be that 6 was like 7. So 267 minus this guy, which is okay. You all you need to know is that it's positive. Right, so this left hand side was more entropically favorable. Then that means this is less entropically favorable than still it's happening, so it's just enthalpy driven. It's driven by enthalpy only. Right, and delta G for this reaction is, well, it's the same value in all of these, and it's, wait, is this positive or negative? Oh god, what was this value once again? Do we have to actually calculate this? So what's this? Okay, it's supposed to be 7, then this is 0, then this is 8. Okay, so 80.7, that is your delta S value, and this is at 298 Kelvin, which is approximately 300. So it's gonna be what? Our delta H is these things, negative 74.9 kilojoule per mole. So you can just say 1000. So negative 74. And in what do you want? You want a kilojoule per mole. Okay, so all right, and then negative T delta S, right? H minus T. So yes, and negative 300. But we want in kilojoule per mole, so divide this by 1000. That times delta S, which is positive for some reason. So sorry, this is negative, right? This is the left hand side 1 second. We want the opposite, so negative 80.7. Okay, so this is just what? Approximately 8. When you cancel this away, when you cancel these away, this is just 3, so it's positive 24. So it's negative 50.9, some near to that. 50.8 works. It's negative. Okay, it's spontaneous. So only ABC will work, sorry, ABD will work, C is wrong, and it's given by enthalpy only. So 12th A, right? Okay, next. So 13, calculate the change in molar Gibbs energy of carbon dioxide at 20 degrees Celsius when it is isothermally expanded from 2 bar to 1 bar. So pressure, oh, it's isothermal. Well, that's very nice. So pressure decreases, that means your volume increases twice that much. And that's just nr nr natural log 2 basically, right? And that's gonna be what's this molar, right? Fine, but you want in Gibbs energy. Okay, you found the delta S for this, delta S per mole, and that's r natural log 2. What is your change in delta H? Okay, so yeah, like what's your delta H? It just changes from isothermally, right? Hey, so if it's isothermal, your delta H is basically 0 because it's, yeah, yeah, basically. So final and initial state would have the same enthalpy as they have the same temperature, right? I'm not saying that it's like, not saying that I used the fact that it's isothermal to say that it's, yeah, I mean I did, because the initial and final point were at the same temperature, but it's not a reversible process. All right, we are not sure if it's reversible or irreversible. So delta S is this thing. Your delta H is basically 0, so this is negative T delta S. So negative T r natural log 2. Okay. Natural log 2, that is the value of delta S, sorry, delta G, right? So yeah, and what will this be? Negative 20 degrees Celsius. 20 degrees Celsius is like 293 point something. No, let's just say it's 300. I like that approximation. Okay, that times R, we want in, okay, kilojoule per mole. So just say it's 8.3 joule per mole per Kelvin, of course, and that times natural log 2, which is 0.7. And we want in kilojoule per mole, so like this is gonna be 0.3. So it's negative 8.3 into into 0.21, I think. Because, yeah. So 83, 83, 0, 6, 16, 3, 4. So yeah, and then how many decimal points? 3. 1.74, but negative, so negative 1.7 something. Right. That's B probably. Right, next. Out of the boiling point, what time is it? 12:19. Fine. Out of the boiling point 1, entropy 2, and pH 3 and EMF of a cell, intensive properties are. So cell EMF, it doesn't depend on how much the quantity, it just depends on the concentrations and stuff. And yeah, so fourth is an intensive property. Entropy is an extensive property because it, okay, if it was like molar entropy or something like that, it would be intensive, but it's entropy, which is extensive because it depends on the number of moles. Boiling point is an intensive property. pH, yeah, I think it is an intensive property because no matter how many times you add the same solution to itself, like if you multiply the solution, it will still be the same. So just depending on the composition of the solution, right? So first, third, and fourth, and that means 14C. 15, which has maximum internal energy at 298 Kelvin. So at, yeah, 298 Kelvin, that's 300 Kelvins. Room temperature. Helium gas, oxygen gas, ozone gas. Internal energy, huh? I mean, okay, how do you measure internal energy? Because these are different gases, and helium gas, how much of the gas is there, that also depends, right? You can't compare 1 mole with 2 moles, or can you? Can't compare these possibly, right? Because internal energy is not a change in some value. It's like it's not doable, right? Oh wait, so like maximum, that means with respect to temperature, it should be at the maximum, like the peak or something. No, that can't be because it will just increase as you increase the temperature. So it means out of ABC, which has more internal energy. That's just stupid. So I'm gonna say 15th. We don't know. It's just a bad question. But if you were to answer it the way that people do, like, take U as NCVDT, even though it's not like that, okay? Sorry, U as NCV times T, not delta T, T. Then look at this. Uh, Helium gas is monoatomic, so it has a smaller CV. Oxygen gas is diatomic, but it's, yeah, it has like 5 rotational degrees of freedom, right? So two rotational degrees of freedom and 3 transitions, so 5 degrees of freedom. So it's more than helium gas, and ozone has 3 rotational degrees of freedom. And yeah, and of course ozone is more energetic than oxygen, I think. C is definitely bigger than B, and maybe B is bigger than A, right? If you use this kind of thing, then you would say C is the way to go, right? But this is just a stupid question because you can't measure internal energy as a function of temperature directly, right? You can only measure the changes. It's the same thing as saying like the potential of ground is 0. No, we define it to be 0, right? You need a 0 mark somewhere, and it's not here. Ethyl chloride is prepared by the reaction of ethylene with hydrogen chloride. Okay. What is the value of delta E if 98 gram of ethylene and something gram of HCl are allowed to react at 300 Kelvin? Oh, so for this, your delta H is constantly this, huh? Okay. What is the value of delta E? Oh, so delta H, that will be just delta U plus delta PV. And so what gram of ethylene? Okay, I understand. So first we need to convert these to moles. So ethylene is just like 2 into 12 plus 2, I think, so it's like 2 into 14. and we are given 98. 98 upon 2 into 14. This will be is this 14? Of course, what else could it be? This is just only 49 upon 14. Huh, weird. That's just 7 upon 2. So 7 upon 2 moles of C2H4 and 109.5 grams of that. So 109.5. So 35.5 plus 1, that's just 36.5. This is like, this times 3, right? So 9, you got 18, and then you got 1.5 over there, and this would just be 109.5. Exactly. So yeah, this is just 109.5. So this is going to be 3. So 7 upon 2 moles of C2H4. So yeah, that's 7 upon 2 moles. Oh, so we have been given delta H, and are we supposed to assume like this goes to completion, right? Till one of them just exhausts at 300 Kelvin. Okay, the temperature won't make a difference unless you give me entropy, right? What is the value of delta E for this reaction? So okay, we'll just say the change in energy per mole of this reaction, which is happening infinitesimally, right? So 7 by 2 C2H4, our system contains right now 7 by 2 moles of C2H4 and 3 moles of HCl, right? Cool. And there's no moles of C2H57, right? We want to find what delta E is. So delta E is delta H minus delta PV, and it's like the pressure constant or something. I don't know. That's not given over there. So delta PV, what do you know? You know that PV for the whole system, that's just nRT, where n is the total mass, sorry, total moles. So this would just be like delta of nRT, and that's just delta n times RT, because we are assuming temperature is constant, right? So they already gave us delta H, negative 72 point what 3 kilojoule per mole, minus, we want to find what this value is. So RT, what is R? Say 8.3, and that times T 300 and delta N. So oh yeah, so like we just want to figure this out for what? For hey, why did you give us the masses if we actually are not going to use them? Because if this is per mole, all we really care about is just like the infinitesimal moles that are like the infinitesimal number of molecules that are reacting. And so this is like not useful at all. Why did we even calculate this? I don't know. Okay, so negative delta n. Delta n for this reaction is negative 1. So that's going to be negative times negative 1. It's positive 1. And yeah, RT basically. So this thing, and we want in kilojoule per mole, so it's like 0.3. That's going to be what? 24 and 3. Yeah, 24 and 9. So 2.49 positive. This plus that. So it's like what? 7. No, it's not 7. 2.3 minus 2.4. Then that's what we have to do. So it's going to be 1, 8, 9, 6. So 69.81, but in negative. That's the value. Negative 69.81. 69, right? Or what else would it be? That is still close to 70. So I mess up something. Your delta n is just negative 1. What else? Yeah. Come on, what went wrong over here? Delta H for this reaction, which is just this thing. Why is, oh, so there's like reaction is also dependent on the concentration then? That is weird. But that isn't it just like PV equal to an RT? So yeah, then It should change just like that. Whatever, that's it. We got it. We got close to it, so A should be the thing. Question number 16, A. Be it correct or not. Question number 17. Question 17 is 2 moles of helium gas undergo a reversible cyclic process as shown in the figure. Assuming gas to be ideal, what is the net work involved in the cyclic process? What? 2 moles of helium gas undergo a reversible cyclic process is shown. So why is this reversible of one thing? I don't know. Okay. Assuming gas to be ideal, what is the net work involved in the cycle? So it's just the the area under the curve, area in the loop. If that makes sense. So right now, like volume increases and then it does this thing. So the work done by the gas, that's just the area. Work done on the gas is negative of the area. So the net work involved in the cycle, it's supposed to be negative, I think, right? It's not having this natural log or stuff. Oh, this is, what is this? It is natural log. Wait, what's this pressure temperature? I thought it was pressure volume. Oh, then that's different. So, oh no, this is bad. So first you have an isothermal process, then you have a constant pressure but changing temperature process. Oh, so you need to write everything in terms of pressure and temperature, right? So for an isothermal process, what is your work? It's just negative nr natural log of V2 upon V1, right? That's the work done on the gas. So you can write this as positive nr natural log of P2 upon P1 because V is proportional to 1 upon P. So yeah, nRT, sorry. So over here, the P2 upon P1 thing is the same, just the temperatures are different, right? So over here, temperature is lower, and that's why this work is a smaller quantity and it's also positive. And over here, the yeah, it's negative, but it's a bigger quantity magnitude. Wow. Tell me what n r natural log of P2 upon P1 is like 2 upon 1 natural log 2 into, say, the first guy's temperature is just 300, the other guy's temperature is 400, but it's a negative because the whole process was opposite now. So it's negative 100 nr natural log 2. That's for these isothermal processes, and for the constant pressure process, you just have to find the volume change, right? So you just want the P delta V thing, which is the same thing as saying like, yeah, it's different, right? So for this guys, the pressure is different and this is different pressure and stuff. But you can definitely write it as nr delta T because, you know, like it doesn't change. So for this guy, the P delta V thing, yeah, like you can write it like that for sure. So it's just delta T for this and then delta T for, so it should be like cancelled out. It's the same in that case. Okay, so no work done in these isobaric processes combined. There's no work done. Is it correct? Maybe it's correct. Yeah, I think so. Right, so like these volumes are different, the pressures are also different. It works out. So it's just negative 100 n r natural log 2, right? And 2 moles of helium, so it's going to be negative 200 r natural log 2. So no, not natural log 4. Okay, then you can write it as negative 100 r natural log 4 as well. That also works. And that's A, 17th A. Question number 18. Question number 18 is 1 mole of an ideal gas is allowed to expand reversibly and adiabatically from a temperature of something. So 300 kelvins. 1 mole. If the work done by the gas in the process is actually draw this thing. So you have 1 mole of this thing, you have 300 kelvins. This goes to, and its adiabatic expansion. Work done by the gas in the process is 3 kilojoule final temperature will be equal to. So you don't know what the final temperature is. Just know what the work is. Oh, hey, so it's an adiabatic process. That just means like heat is zero. So the work done is also the change in entropy. Sorry, the change in energy. Yes. So the work done by the gas is this thing. That means it lost that much of energy. So now energy change must be negative 3 kilojoule. Right. Hey, CV is given. That's very nice of you. Right. Just 20 joule per Kelvin, so whatever. So yeah, like 20. That's our CV. N is just one. That times delta T. Delta T. That is the work done. Sorry, that's the change in the energy of this thing, and that is just negative 3,000 joule. Yeah. So delta T is just negative 150 Kelvin, like that. And initially it was at 300, so now it's gonna be at 150 Kelvin. Boom. For like 18th C. 27 degrees Celsius is definitely just 300 Kelvin. 18th C. Two moles of an ideal gas compressed adiabatically against constant pressure of 2 atmosphere, which was initially at 350 Kelvin and 1 atmosphere pressure. The work involved in the process is 2 moles of an ideal gas n equal to 2. CV is 5 by 2 R. Okay. Compressed adiabatically. Adiabatic. It's compression, that means V2 is less than V1. Against constant pressure of 2 atmosphere, which was initially at 350 Kelvin. Okay, and 1 atmosphere. So this thing is P2, right? So is this like a reversible adiabatic or is this just adiabatic? But it's constant pressure, yes. So like P external is 2 atmosphere, it's not P2. Right, initially it was just a pressure 1 atmosphere. So from this you can find like moles or so. No, you already know it's just 2 moles. You know like the moles, the CV, what is V1 and V2, we don't know that. We know what the initial pressure was, what the temperature was. So like we can figure out what the volume was. Okay. And it's adiabatic. Okay, that means whatever work they did, that was just the change in temperature. You don't know what the final temperature is, just know what the initial temperature is. That's all you know. Uh, but it could have stopped any process. Then how am I supposed to do this? You know what the initial pressure is. You know what the initial what you know everything about the initial state. But it was adiabatic, constant pressure of 2 atmosphere. We don't know anything about the final state. So it's like pretty much just impossible to do it. Yeah, there's nothing even about the final state. If you don't give me the final state, I cannot solve it unless I assume it's reversible adiabatic. But then it makes no sense for it to be at constant pressure of 2 atmosphere, right? Because adiabatic it changes. It's like PV power gamma equal to constant. This makes no sense, you know. So work done is a change in the temperature. If your final state is like that, okay, fine. Then come on. Fine. What do you know? You know, like P delta V, P external, of course. Delta V, that's our work done. That's also the change in the like energy, which is NCV delta T. Now, how do you find delta V? So that's where you can figure out what V1 is. Do you know what the other thing is? No. If it's a constant pressure of 2 atmosphere and just like compressing it, after a point, like the inside pressure, that will become 2 atmosphere, right? Or will it not? Do we just like stop somewhere, or do we keep on compressing? Because we could keep on compressing and then do more work on it, and then it's just impossible to find it like that. So we will say keep on compressing till it becomes 2 atmosphere. So from that we can say like P2 is the same thing as P external, it's the same thing as 2 atmosphere. This is a ambiguous question. Right, so we compress it till we cannot anymore with the same pressure. So now we know P2 and we don't know what V is, right? But we do know that P external times V, that's the same thing as NR T final, right? So like NR T final, or let's say T2, right? Minus P external times V1. We can figure out what V1 is. That's nice. NCV times T2 minus NCV T1. We know what T1 is. So from this, you can say like NCV minus R T2. That thing is just NCV T1 minus P external V1. And now how do you find V1? So V1 is just nRT1 upon V1. So now let's rewrite this equation. NCV, we just gave us is like 5 by 2 R, so it's 3 by 2 R T2, that is the same thing as NCV, so N into 5 by 2 R T1 minus this guy, so P external is just 2 atmosphere and P1 is 1 atmosphere, so P2 upon P1, that's 1. So this thing is just N, so like 2 N R T1, like that. Oh, so from this we can figure out what T2 is in terms of T1. Okay, that's nice. So yeah, like this will be 3 by 2 T2 equal to 5 by 2 T1 minus 2 T1, which is 1 by 2 T1. So that means T2 is just 1/3 of T1. Hey, that's nice. And we know what T1 is. Is this actually correct? Because okay, yeah, it looks correct. So that's the thing. T2s is that. So now we can figure out what you're gonna find actually. Final temperature will be good. That's exactly what you're gonna find. So it's just 1/3 of T1, and initially it was what? Question number 19. Sorry. The work involved in the process, not that. It was initially at 350. Work involved in the process. Fine. It's adiabatic, it's the same thing as that. So it's like 2/3 of T1 into NCV. How many moles? 2 moles. So 2 into CV is just 5 by 2 R. That is the work involved. Oh, so like we can submit directly in terms of R. Well, that's nice. Hey, yeah, that's very nice. So this is gonna be what, like 10 upon 3 into T1 times R. So like 3500 upon 2, that times R. So something like 1717500, something like that. And that's not there, of course. I don't know how this is supposed to be. Okay, just move on. Maybe I did some mistake somewhere. Question number 20. I'll do it once again after we are done. Maximum efficiency of a heat engine operating between 100 degrees Celsius and 25 degrees Celsius. Right. This is our heat engine. This is your what, like 100 degrees Celsius. So what in temperature? It's 373 Kelvin. And this thing is your like 25 degrees Celsius. So that's like approximately 300 Kelvin. This is like 375. That's just for calculation purposes. Right. And you put out some work when heat passes through it. So what's the thing? Like this heat engine's entropy doesn't change when it does a cycle, then that means the heat that went inside of it, so Q in, and the heat that went out of this engine, they must produce no entropy changes for the universe, right? And of course, W is just Q in minus Q out. What do you know? You know, like Q in upon 375 should be equal to Q out upon 300, so that no entropy, basically like Q in minus Q in upon 375 plus Q out upon 300 equal to 0, right? Because delta S universe should be 0, and that means Q in upon 375 equal to Q out upon 300, of course. And what is Q in? It's just Q out plus W. What do you want to find? You want to find the efficiency, which is just W upon Q in. So write Q out as W minus Q in. There we go, we got it. So that's 300 upon 375 minus, sorry, plus 1, right? Because, sorry, it's supposed to be Q in minus W. Yeah, then this thing is like 1 minus this guy. Right? So do the calculation. This becomes Q in equal to W. Right? This goes over here. This comes like that. Multiplied by 300 and stuff. Of course. Yeah. Then your efficiency is just this value. So it's 75 upon 300. See, the simplification does work. And 75 is just like 25 times 3, so it's 25 on 100, so that's just 1/4, 0.25 basically, or like 25%, so 20C. Let's just do 19th once again, and then I'll stop the video after doing 19th once again. Right, so let's do it once again. Your initial, you just have n equal to 2, CV is 5 upon 2R. Okay, adiabatically against constant pressure of, so P external is 2 atmosphere, and that means P2 is also 2 atmosphere, and P1 they gave that as 1 atmosphere. T2 we don't know what is. T1 is 350 Kelvin. Okay, V2 we don't know what that is. V1 we know that for sure, that's just nRT. So nRT 1 upon E1, like that. Alright, now let's try to do it once again. So P external times V2 minus P external times V1, that thing is the same thing as, so this is the work done on it. Or we should go the opposite way, because now V2 will be smaller, we know that for sure. Right, so work done on that guy. Right, because, wait a second, is this the thing? V1 is a bigger quantity, isn't it? And yeah, so like the external into V1 minus V2, that's the work done on the gas, of course. Right, negative PD, not positive PD. This is equal to NCV delta T, and that's just like NCV T2 minus NCV T1. Now we can write it differently. So P external, okay, this is the same thing. P external we can write as P2, and then P2 V2, that's just nRT2. And we know what, like we know that P external right now is just 2 times of P1, right? And then like for this case only, it's 2 times of P1. Then we can write this thing as nRT1. So cancelling of the R's and N's, you can basically say like 2T1 minus T2, that was 5 by 2 T2 minus 5 by 2 T1. So basically 4 T1 minus 2 T2 equal to 5 T2 minus 5 T1. So yeah, that means this is what? This is T1 minus T2. This is T2 minus T1. Is that correct? I think so. Okay, so that means 91 equal to 72. So we can find out what T2 is. T2 is just 9 upon 7 of T1, which, oh, now it matches because 350, that's why they gave us like that. So 9 into 50, which is 450. Yeah, I think this was the problem. I just switched the order over here, and that's why I was getting some really bad stuff. So now we got T2, we can definitely figure out what T work done. So work done is the same thing as change in energy. That's just NCV. So 2 into 5 upon 2R into delta T, which is like 540 minus 350. Sorry, yeah, 450 minus 350, 100. That's 500 R there, which is D. Right, so 20 questions done. Let's check. There's a lot that we have to do if we wanna do it completely. But then I'm just doing it for practice. So this is not what I was doing. Answers getting it to IDJ. So we did till 20 questions. What level was this? Oh, this was just needs level, I think, because yeah, advanced level is different. Then I just need 20 questions of main level. Oh, that's very sad. I should have talked less. I should have talked less. Okay, first A, second A, third C, fourth D, fifth C, sixth D, seventh A. Come on. Okay, eighth. B, D, A, C. 12th, ADC. 15th, CCAC. Wait, what? 16th is C. So, okay. 17th is A. 18th C. Then D and A. Y. Okay, let's see what went wrong. Number 16. Where is it? Okay. Question number 16. So they gave C as the thing. So it's negative 209.4 delta E value. Why? So does it matter how much of these react? Maybe it does matter. So like they want us to do it till completion? No. Okay, if they gave us units, then we would have understood what they want. So like this was just 7 by 2 and what 3 HCl, so then only 7 by 2 of that. So maybe 7 by 2 into 64.81, that's just 7 into 3, 2.405 something. So that's 3, 2.4, which is 8 to get it on 14 into 6, and that's just 1. So 21 is like 2 to 6 point that, and oh, and like 16th C is correct, that's 209.41. How does that even make sense? Oh, I remember we didn't exactly get like 64.81, we got something else, and yeah, something different. We got like 69 or something, right? But that would be even bigger than this. So how does it should make sense? I don't know, because this doesn't make any sense. Why would you want to do this till completion? It will change, right? Yeah, I mean, isn't this like kind of a reversible reaction basically, because both of these are gaseous? And so what if this is an irreversible reaction in total? But still, like it changes, its delta G value changes as you change the concentrations. So how does it even make sense? I don't know. Just put a very wrong question. Like this does not make any sense. First they give delta H in kilojoule per mole and in kilojoules, so no mole over there, and they expect you to give answers in terms of kilojoule and not kilojoule per mole. And it doesn't make sense because actually, like, if you complete the whole reaction, then that delta E will be different than the delta E that you get for the infinitesimal reaction, right? So no, it doesn't make sense. It just doesn't make sense. Anyway, right? Because then of course, like, PV will be different as well, right? So you're changing from some pressure to some other pressure. Yeah, PV will be different, and that's why you get these two different answers. I get it, but they should have told to do it till completion. I just did it for an increasing reaction. Whatever. 20. The maximum efficiency of a heat engine. So they gave A as the correct thing. Okay. 100 degrees Celsius and 25 degrees Celsius, the maximum efficiency of. But I did get C, Like, just, I'm going to not do it once again. It's like, this is 373 Kelvin, and this thing is. Okay, 25 degrees Celsius, like approximately 300 Kelvin. This thing is 375, of course. Right? And then you just have heat going in that way and that way, and this is like work going in that. So this thing is, say it's Q2, this thing is Q1, then you just have Q2 upon 375 equal to Q1 upon 300, but then Q1 is the same thing as Q2 minus W. That goes over here, just 300 right there. So W is Q2 minus 300 upon 375 times Q2, which is the same thing as 75 upon 375 Q2. Oh god, yeah, that went wrong. I took it as 300 and not 375. That's where it went wrong. And now what's this efficiency? Like this upon Q2, that's gonna be this efficiency. So that is 25 upon 125, which is 1 upon 5. That is in fact 20%. So 20 was a silly mistake, and 16, it's their mistake. They didn't give the question completely right. So yeah, I'll see you guys in the next video.